All right, welcome to the video that introduces you to the Euler method, or that shows you how to do it. So here's a sample differential equation that I'll do it on, and here's the general setup. X prime equals function of x and t. So for the whole thing, you saw that we need some kind of time step. So let's fix that time step value. Let's call it delta t. And, since this is supposed to be a more explicit example, let me just choose it to be 0.001 or something like that. But this is something you would want to put at the top of your code and then modify it and look at how it affects things. If you make it really small, then you'd have to run your code for a very long time to predict x of 10. So okay, and one other thing I want to do is, so here I chose this example since no one chose this as their project, since I disallowed it. But I realized now that this is a little bit too simple of an example, since the general setup has x prime possibly depending on x and t in the differential equation. So let's just add a minus t here for fun. So before I put the minus t, it was like a population growth or something like that, assuming r is assuming r is positive, then it's population growth. If I put minus t, then it's like there's some constant rate of death which is increasing. So maybe x is the number of people at time t, and then this term represents that there's some monster that's eating people or something, and the rate at which it eats people is increasing linearly. So on the first day it eats one person, on the second day it eats two people, and so on. Okay, so it's a stupid example, but hopefully enough to show you, to demonstrate the idea. So let's make a table, and the idea is to fill out the table as we go along. And I'm going to do this both in general and in the example. So I'm going to have a time column, and at each time I'm interested in knowing about x and about x prime. Actually, I'm really only interested in knowing about x, right? But because I'm stuck with this differential equation, I'm forced to get x prime into the picture. So if I want to predict how x is going to change, I'm going to have to use x prime. Okay, so there's one row of the table where I know perfect information, which is that at time 0, x of 0 is x naught. So I've got perfect information at that time. Now, what about x prime? Do I know how x prime starts out? Yes, because I know that x prime is rx minus t at any given time t and at any given x value x. And if time is 0, and the x value is x naught, then this right-hand side evaluates to rx naught. So rx naught is x prime at time t equals 0. And in more generality, what we're doing is we're just taking the right-hand side and plugging in x naught and 0. Then at time, okay, so this is the row, the initial condition row, where we have perfect information. Nothing about this is an approximation yet. It's perfect, because that's that's what we prescribed as the initial condition. Now we're going to make an approximation at time, the original time plus delta t. So we're going to make one step. And then after that, we'll make another step. So we'll be at 2 delta t, and then 3 delta t. So 0.002, 0.003, and so on. So how do we predict what is the value of x at time delta t? Well, dx dt is the instantaneous value for what we might call delta x delta t. It tells us how x changes every time t changes. This would be an approximate version of this. So the definition of this derivative is that it's the limit of these as the delta t becomes very small. So that's the idea that we're going to use. So what goes here is the new x. So focus on, let me put it this way, focus on this step here. How do we go from having this filled out first row to a filled out second row? And what's the new x? So let's call it x1 to start with. And the question is, what is x1? All the other things were given in our problem. So we know r, we know x naught. But what should x1 be? Well, x1 minus x naught, that's the delta x. That's how x changes from time delta t, from time 0 to time delta t, right? So as time goes from 0 to delta t, this is the time difference, and x changes from x naught to x1, and I'm trying to figure out what is x1. So this is approximately, and the approximation is good insofar as delta t is small, it's approximately dx dt at any t at 0 or at delta t. At 0 is where we have information at the moment, so this is what it approximately is. And this we already have a value for here. It's r x naught, right? Or in a little bit more generality, it's f of x naught, 0. So let me just put in r x naught. So then, if I want to know x1, I can solve for it in this approximate equation. Multiply both sides by delta t, and then add x naught to both sides. So x1 is x naught plus that times delta t. And this equal sign should be wiggly. So this is like a first order Taylor approximation, right? This is where the idea of a first order Taylor approximation kind of comes from. It's saying the new x is the old x plus the rate at which the x is changed times the amount of change, right? So new x is the old x plus the expected change in x, the approximate change in x. So then here, I can fill in what is the new x. It is the old x plus the instantaneous rate of change of x at the previous time, so this, times the time step. So what I'm going to put here is whatever I had here. So this thing, I'm going to put there. So this is my approximation. This is my sort of x1. Let's call this x1 actually to make things a little bit easier. So there's x1. And in a little bit more generality, I'm saying let's define x1 to be x naught plus the expected instantaneous rate of change of x, or what was the instantaneous rate of change of x at the previous time, times delta t. So it's this going here. So this is going here. Okay, and now you've seen one sort of iteration of the of the algorithm. The next, from here on out, you just repeat. So I'll show another one. So how do we find out what is x prime here? Well, it's whatever this is, whatever this evaluates to for the current time and the current x, for the current t and the current x. So that's rx1 minus, and what's time? Currently it's delta t. So here it's f of x1 comma delta t. And now we can use that to make a prediction as to what the next step is going to be. So let's see. This is going to be x2, and I'm wondering, what is x2? Well, what changed from, now what I'm interested in is sort of this step. What changed from here to here? So x changed from x1 to x2, and t changed from delta t to 2 delta t. So in this kind of analysis that I was making here, I'm looking at the change from x1 to x2, so this is the difference. This is how much x increased by from x1 to x2, or decreased if it ended up being negative. And the time is going from 2 delta t to, from delta t to 2 delta t, and this is the total change. So, and we are approximating this now by not dx dt at time 0, but dx dt at some time between delta t and 2 delta t. Well, we only have it at time delta t. So this is what goes here, and that will be r x1 minus delta t, right? So that's what we put there. And so the idea is that new x equals old x plus the now updated rate of change of x, so updated to this, times the change in time, which is still delta t, right? 2 delta t minus delta t is still delta t. So new x is old x plus, so you see how it's pretty good that I gave this a name, x1. Otherwise, here I'd have to rewrite this entire complicated expression, and things will get more and more complicated as you go down the line. But since I just called this previous step x1, I can just write x1 here, and then something times delta t, where the something is the instantaneous rate of change that I previously had, which is this one. So I just take this and stick that there. Rx1 minus delta t. And in general, in more generality, what's happening is new x equals old x plus rate of change times delta t, where this is the rate of change. So this is going here. F of x1 delta t. And then we keep going. So let me just pause the video, fill out the next one, and unpause so you don't have to sit through it. All right, so I filled it out here. So the next x prime would be x prime evaluated at yeah, I had not filled this out before I paused, right? So the next x prime would be x prime evaluated at this t and this x, which I called x2. So it's rx2, which simplifies to, which evaluates to r times this thing. So it's actually something quite complicated. So r times x2 minus 2 times delta t, which is the t that goes here. And then I use that to make another step. So new x equals old x plus the previous derivative, the previous slope times delta t. And here's the sort of general version. If I have time 2 delta t and x value x2, then the derivative is f of x2 to delta t. Then I can use that to determine what is x3. It's x2 plus the slope times the delta t. And so on. You can keep going. So one thing to notice is that when you're putting this into a computer, you actually have to put numbers in if you want it to compute, if you want it to fill out each row of information and have numbers each time. So having this r be unknown is not going to work if that's how you're trying to do things. And having the x naught be unknown is not going to work. So x naught would have to be a specific number, r would have to be a specific number, and then you can do this. Then here you would have an actual number. Here, r times x naught, that would be an actual number. Then this row of the table, t would be a number, x would be a number, x prime would be a number. Then you could compute x1 and you would get an actual number, right? And this would be an actual number. So each time, and delta t is a number that you choose at the beginning. So each step, this will be like a loop, right? You'll make your program go through a loop filling out each row. At each step, you have actual numerical values for all of the different parameters, for all the different variables, x and t, and x prime. That's why it's numerical analysis. Okay, so now I think you've seen everything you need to see to do this portion of your project, or to at least try it and start exploring, except for how to do the actual coding part, if you do it by coding. So I'm going to make the rest of this lecture kind of a choose-your-own-adventure lecture, where hopefully you have watched this video, and then the next video is going to be just one, and you choose which one you want to watch. So start each one, and it'll tell you what this one is going to be about. Then either watch it or skip to a different one. And in each of the next videos, I'm going to show you how to code up this thing in a particular way. Well, I'll just tell you right now what the different ways I have in mind are. So for one way, I'm just going to use Python. And I'm going to use that as kind of a catch-all for all basic scripting languages, coding languages that you want to use. Like MATLAB, if you're familiar with MATLAB or Octave or whatever, go ahead and use that. The ideas you see in the video where I use Python will probably be similar. You just have to use different syntax, and well, there are probably more different things, but whatever. So I'll just do something basic with Python. And I'll do something with Mathematica, which will probably look very different. And I'll do something with Excel, although I'm not going to use Excel, the program. Let me just say spreadsheets. So this is the least coding way of doing it, where you literally just have a table and you fill out the columns. But it is kind of like coding. Okay, so I'm not saying you have to do it using one of these. I'm saying whatever you choose to do, either figure it out on your own or choose to do it using something similar to one of these, and then pick the most similar video and choose that. That will probably help you somehow.